Hi, this is Nastianevsky. We're doing this class's discrete structures. We're doing section 3.1, which is about relations. We're doing these problems. Okay. As always, you should first do the problems and then check your answers here. Don't watch me do the problems because that's just a waste of time. Okay, great. Okay, so there's a lot of work here. There's a lot of problems, and we got to get through them. So it starts off with a set 0, 1, 2, 3. Okay, and it has some relations on these sets, 5 different relations, and it asks you, are these relations reflexive, anti-reflexive, symmetric, anti-symmetric, and transitive? Okay, so I put them up already. I put up what the ordered pairs are. Okay, so m plus n is equal to 3. Okay, so for what m and n do you have this that m plus n is equal to 3? And the answer is these things. Okay, so first of all, are they reflexive? Well, the answer is no. There's no 0, 0, 0, 1, 1, 2, 2, 3, 3. So it's not reflexive. Is it anti-reflexive? Yes. There are no 0, so yes, it's anti-reflexive. Is it symmetric? Yes, because if it's 0, 3, the main idea is that plus is symmetric. A plus B is equal to B plus A. So if 0, 3 is in there, then so is 3, 0. If 1, 2 is in there, then so is 2, 1. Okay. Is it anti-symmetric? Which means if 0, 3 is in there and 3, 0 is in there, that does not mean that 0 is equal to 3, and the answer is no. Is it transitive? I think the answer is yes, because, oh no, it's not. If 0, 3 is in there and 3, 0 is in there, that doesn't mean that 0, 0 is in there, so it's not transitive. Okay? M minus n is even. Now, here it depends on your definition of even. Is negative 2 even, yes or no? Okay? So we're going to say no for a minute. And then we have 3 minus 1 is 2. 2 minus 0 is 2. 3 minus 3 is 0. 2 minus 2 is 0. 0 is even. 1 comma 1 minus 1 is 0. 0 comma 0 is even. Okay, so that works. So this is the answers. Now, if you say that negative 2 is even, then 1 minus 3 is even, and 0 minus 2 is even. Let's, for the hell of it, say that it is even. Okay, good. Negative 2 is an even number. Okay, great. Is it reflexive? Yes. Why? 0, 0 is in there, 1, 1 is in there, 2, 2 is in there, 3, 3 is in there. Good. Is it anti-reflexive? No. Is it symmetric? Yes. If 3 1's in there, then so is 1 3. If 2 0's in there, then so is 2 2. If 3 3 is in there, then so is 3 3, etc., etc. So it's a symmetric. Is it anti-symmetric? Well, 2 0's in there and 0 2's in there, but 0 is not equal to 2. 3 1's in there, 1 3 is in there, but these two are not. So let's go through that. So it is not anti-symmetric. Is it transitive? I think it is. I think it is. Okay, 2 0 0 2 0 2 2 0 0. So I think it is. Okay, m less than n. A lot of things here. So first of all, less than or equal to. As soon as you have equal, that means 0 0 1 1 2 2 2 2. So it's reflexive. Is it anti-reflexive? No, it's not anti-reflexive. Is it symmetric? If m is less than n, does that mean n is less than m? No. 0 is less than 1. 1 is not less than 0, so it's not symmetric. Is it anti-symmetric? Okay. Well, yes, it is anti-symmetric. I just have to explain why. Look, if m is less than or equal to n, and n is less than or equal to m, the only way that that can be is if they're m is equal to n. So the only way you have both sides to be true is these 4 times. So it is anti-symmetric. I could be wrong on there. If I am, look at the comments on the bottom. See if somebody's going to correct me. Okay, next is a transitive. If m is less than n and n is less than p, is m less than p? And the answer is yes. So 0 is less than 2. And 2 is less than 3. Therefore 0 is less than 3. 0 is less than, anyways, it is. 0 is less than 1. And 1 is less than 3, so 1 is less than 3. 1 is less than 3. Why didn't I write that? Oh, there it is. 1 is less than 3. So it is transitive. Next. M plus n is less than 4. M plus n is less than 4. Okay? First of all, is it reflexive? 0, 0, 1, 1, 2, 2, not 3, 3. So it's not 3, 3, therefore it's not reflexive. Is it anti-reflexive? No, because 0, 0 is in there, 1, 1 is in there. Is it symmetric? If m plus n is less than 4, then again, by the commutativity of arithmetic, n plus m is less than 4. So yes, it is symmetric. Is it anti-symmetric? Okay, let's go through that. 0, 2 is in there, 2, 0 is in there, but does that mean that 0 is equal to 2? And the answer is no. Is it transitive? If m plus n is less than 4 and n plus p is less than 4, will m plus, anyways, the answer is no. I'll show you. 0 plus 3 is less than 4. 3 plus 0, no, sorry. 3 plus 0 is less than 4. 0 plus 3 is less than 4. But 3 plus 3 is greater than 4, so it's not transitive. Okay? Finally, max. Max of m comma n is equal to 3. Okay? Is it reflexive? No. 3 plus 3 is in there. 3 comma 3 is in there. Oops, I did that twice. Okay, 3 comma 3 is in there, so it is not reflexive. 0, 0 is not there, 1, 1 is not there, 2, 2 is not there. It's not anti-reflexive either because 3 comma 3 is in there. Is it symmetric? Yes, because the maximum of m and n, it doesn't matter how you put them in, is the same as the maximum of n comma m. So yes, it is symmetric. Okay. It's not anti-symmetric. 2, 3 is in there, 3, 2 is in there, but 2 is not equal to 3, so it's not. Is it transitive? No, it's not. 1, 3 is in there, 3, 1 is in there, but 1, 1 is not in there, so it's not transitive. Okay, so that's nice. Great. It's a nice way of doing things. Okay, let's go to problem number 2. Okay. Okay. A equals the set 0, 1, and 2. Okay. Each of the statements below defines a relation R by m comma n if the statement is true for m. Write each of the relations as a set of ordered pairs. Okay, so it's basically the same thing, but just with different ones. So this is problem number 2, and we're going to do the same thing as we did before. Okay. Okay, let's do it. M less than or equal to n, m less than n, m equal to n, m times n equals 0, m times n equals m, m plus n is a member of A, m squared plus n squared is equal to 2. M squared plus n squared is equal to 3. And m equals max of n comma 1. Whew. Painful. Okay, let's try to make it neat. Okay, so they want us to go through and tell us which of there are 9 possible relations in here. We should really write down them, but we can do it like this. Okay, so let's do it. You ready? 0, 0 is in there. 0, 1 is in there. 0, 2 is in there. 1, 1, 1, 2, and 2, 2. Okay, great. 2 is less than 2, less than or equal to 2. Okay, this is a subset of this because it doesn't have equal. So it's just going to be 0, 1, 0, 2, 1, 2. Great. M is equal to that, and that's easy. 0, 0, 1, 1, 2, 2. That's it. M times n is equal to 0. The only way you're going to get 0 when you're multiplying is if there's a 0 in there. So it's basically 0, 0 is in there, 0, 1 is in there, 0, 2 is in there, and 1, 0 is in there, and 2, 0 is in there. Okay? M times n is equal to m. The only way that's going to happen is if n is 1. When you multiply, so it's basically, oh, can't be, oh yeah, that could be 0. 0, 0 is in there. Sorry, I was wrong. 0 times 0 is there. 0 times 1 is 0, so that works. 0 times 2 is 0, so that works. 0, okay, now 1 times 1 is in there, and 2 times 1 is in there, and that's it. Okay, next. M plus n is a member of A, so let's do it. Ready? 0, 0 plus 0 is equal to 0, that's good. 0, 1 is equal to 1, that's good. 0 plus 2 is equal to 2, that's in there. 1, 0 is in there. 1, 2 is in there. No, stop. 1, 1 is in there. Okay, and 2, 0 is in there. That's it. 2, 1 is 3. 3 is not in the set. Okay, let's do this. I'm going to write down all 9 of them, and then we're going to check off what's in there. So let's just write down all 9. 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. Okay, that's all 9. So let's see. Those squares, 0 squared plus 0 squared is not equal to 2, so it's not in there. 0 squared plus 1 squared is not equal to 2. 0 squared plus 2 squared is not equal to 2. It's nothing. 1 squared plus 1 squared is equal to 2. So that's good. No, 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 no. Great. What about here? M squared plus n squared is equal to 3. How do you get 3? Let's see. No, 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 no. 1 squared plus no, 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 no. Empty. Okay. And finally, the max of n, 1 is equal to m. So it says. Oh, that's hard. Okay. The max of 0 and 1 is equal to, no. The max of 0 and 1 is equal to 0. No. The max of these two, no, of 2 and 1 is equal to 2. No. The max of 1 and, 0 and 1 is equal to 1. So that's in there. Let's do that again. The max of 0 and 1, n is 1, is equal to 1. So that's there. Okay. The max, so this is in there. The max of 2 and 1 is 2. All these are going to have 2 in there. I think this is in there too. Okay, not sure about that. Great. That is the answer. Okay, now let's do what they asked. Question number 3 says, which of the relations in exercise 2 are reflexive and symmetric? Okay, so let's go through them. So this is question number 3. Okay, reflexive, 0, 0, 1, 1, 2, 2, yes. Symmetric, 0, 2 is in there, but 2, 0 is not in there, no. Oh, by the way, you can see it's reflexive because there's an equal sign there. So when the two are equal, this is. Okay? It's not symmetric because if m is less than n, it doesn't mean that n is less than m. Okay. Is it reflexive here? No. Is it symmetric here? No. How about here? When they're equal? Yes, it's definitely reflexive. Everything is itself. And it's symmetric also. Okay, good. Is it reflexive? Okay, is this reflexive? 0 is it? No, it's not reflexive. Is it symmetric? Yes, because m times n is the same thing as n times m. So it is symmetric. So it's not reflexive, it is symmetric. Okay, this is a little bit more complicated. Let's do reflexive. 0, 0, 1, 1, yes. No, not, it's missing 2, 2, so it's not. Is it symmetric? And the answer is no, because 2, 1 is in there, but 1, 2 is not in there, so it's not symmetric. Okay? Is it reflexive? No, because 2, 2 is not in there. Is it symmetric? Yes, because m plus n is equal to n plus m. So if m plus n is a member of A, then so is n plus m. So symmetric, yes. 0, 1, 1, 0, 0, 2, 2, 0. Okay, so it is symmetric. Okay. This is not reflexive because 0, 0 is not in there and 2, 2 is not in there. Okay, it is symmetric because if 1, 1 is in there, then 1, 1 is there. Okay, good. Okay, this, is it reflexive? No, it's not reflexive. Is it symmetric? Yes, it is. Technically it is, because if 0, 0 was in, if something was in there, then the opposite would be there. Okay? We'll deal later on with this. I think when we get to problem number 13, we talk about the empty relation. Okay? This has 1, 1 and 2, 2, but it doesn't have 0, 0, so it's not reflexive. Is it symmetric? It has 1, 0 in it, but not 0, 1. So it's not symmetric. Okay? So that takes care of number 2 and 3. Great. Number 4. Okay, number 4 is more of this, but here we have an infinite sets. So we're dealing with the natural numbers, and we want to write the relation R1 as pairs such that m plus n is equal to 5. Okay, R1 is equal to m comma n such that m plus n is equal to 5. Okay, so let's write that out. Okay, we should do it really the same way. Okay, so let's do this. You ready? But so the main point is this is infinite. So this is equal to the set, let's see, equal to 5. How do you get 5? 0, comma 5 is there. 1, comma 4 is there. 2, comma 3 is equal to 5. 4, comma 1 is equal to 5. 5, comma 0 is equal to 5. Can't think of any other way. Okay? Great. So this is part A. Part B. Okay, do the same for max of m comma n is equal to 2. Our 2 is equal to m comma n such that max of m comma n is equal to 2. Okay, so this is equal to, okay, what numbers, you plug them in, you get the max is equal to 2. So this is going to be, let's see, 0, comma 2 is in there. 2, comma 0 is in there. 2, comma 1 is in there. 1, comma 2 is in there. And 2, comma 2. Anything else is going to have a higher number, and you're not going to have it. And the maximum of anything higher is higher, so that's not going to work. Okay, great. Number C. Okay. Okay. It says as follows: the relation R3 defined by consists of infinitely many ordered pairs. So R3 is equal to the same thing, order m comma n, such that min, not max, min, of m comma n is equal to 2. Same thing, but instead of min, max, we have min. So they says there's an infinite pairs, but they just want to write 5 of them. So let's do it. You ready? 2, comma 3. The minimum of 2 and 3 is 2. The minimum of 3 and 2 is 2. The minimum of 4 and 2 is 2. The minimum of 2 and 4 is 2. The minimum of 5 and 2 is 2. The minimum of 2 and 5 is 2. The minimum of 857 and 2 is 2. The minimum of 2 and 857 is 2. So, dot, dot, dot. Works like that. Okay, just for the hell of it, it wasn't assigned in homework, but let's do 5. Problem number 5. It says, question, are these reflexive, anti-reflexive, symmetric, anti-symmetric, transitive? Let's go through each one of these. Okay, is this reflexive? No. Is it anti-reflexive? Yes. Nothing there. Is it symmetric? M plus n is equal to n plus m. Yes, it is. Is it anti-symmetric? No. 1 plus 4 and 4 plus 1, but 1 is not equal to 4, so it is not. Is it transitive? And the answer is no. 5 plus 0 and 0 plus 5 is in there, but 5 plus 5 is 10, so it's not transitive. Okay, numbers, let's do this one. Is this reflexive? The answer is no, and there's no 0, 0, there's no 1, 1. Okay, so it's not reflexive. Is it anti-reflexive? No, because it has a 2, 2 in there. Okay, is it symmetric? Yes, because max is a symmetric function. Max of mn is the same as n, max of n comma m. So it goes both ways. So it is symmetric. Is it anti-symmetric? No. Maybe. No, it's not anti-symmetric. Is it transitive? 1, 2 is in there, 2, 1 is in there, but 1, 1 is not in there, so it's not. Okay? Okay, let's do this. Is this reflexive? No. Is it anti-reflexive? Certainly seems that way, although you would think 2, 2 is in there. I'm sorry, 2, 2 is in there. So it's not anti-reflexive. Is it symmetric? And the answer is yes, it's symmetric. Is it anti-symmetric? No. Is it transitive? Absolutely not. 857, 2 is in there. 2, 857, but 857, 857 is not, so it's not transitive. Okay, so we did 5. 5 is a bonus question. We didn't even ask for it, but we did it. Let's do number 7. Define the divides relation. Okay, m, n, let's just go through this. m/n means n is a multiple. N is a multiple of m. Another way of saying it is m divides evenly into n. Good. It's just another way of saying it. Good. Okay, great. So we're talking about this. The relation R, which is equal to those m, n, such that m divides into n. Great. And now we want to know, is it reflexive, anti-reflexive, symmetric, anti-symmetric, and transitive? Okay, so let's go through it. Question: does 3 divide into 3? Okay, and the answer is yes. Does 5 divide into 5? The answer is yes. Does 25 divide into 25? Yes, it is. So it is reflexive. Every number divides into itself. Is it anti-reflexive? Well, if it's reflexive, it's not anti-reflexive, so it's not anti-reflexive. Is it symmetric? If 3 goes into 15, does 15 go into 3? And the answer is no, it doesn't. Is it anti-symmetric? If the only way m goes into n and n goes into m, the only way that can be is 5 goes into 5 and 5 goes into 5. That's the only way. So then those two numbers are equal. So yes, it's anti-symmetric. Next, exactly, evenly. Okay, is it transitive? You ready? Look, if m goes into n and n goes into p, if m evenly divides into n and n evenly divides into p, so let's do an example. 3 goes into 15 and 15 goes into 45, then 3 goes into 45. So yes, it is transitive. Okay, so that's the first part. Next, describe the converse relation. Okay, are this. Okay, so basically you can say it as follows. This is pairs n, m, such that, okay, now we need a better way of saying it, such that what? Well, m is a multiple of n. So let's go through it. Okay, 3 goes into 15 in R. Okay, 15, so we say 3 is related to 15. Okay, 15 is related to 3 because 15 is a member of R back arrow. So I got this wrong. Okay, so 3 goes evenly into 15. 3 goes evenly into 15. So let's do this. Okay, so this is the way that. So 3 goes evenly into 15. 15 is a multiple of 3. And that's true. Okay, so that's the way you describe it. So this is the way you describe R. N is a multiple of M, and M is a multiple of N. This is the way you describe R back arrow. Okay, which of the properties does the converse relation satisfy? Well, let's go through it. R, anti-reflexive, symmetric, anti-symmetric, transitive. Okay, look, if M comma N is in here, then it's also in here. Okay, this is not no ordered pairs. It's not symmetric, and if you switch them around, they're still not symmetric. Is it anti-symmetric? Yes, it is anti-symmetric. Is it transitive? Yes. Let's go through it. If M is a multiple of N and N is a multiple of, so it's anti-symmetric. So yes, it works. Okay, so that was number 7. Okay. Okay, number 9. This is the one I said 13, but this is number 9. Number 9 is about the empty relation. Okay, and here we really have to get into the nitty-gritty of the definitions of what those properties are. So let's do it. We have 2 parts. Okay, S is a non-empty set. S is, so this is number 9. S is a non-empty set. Okay. Okay. And the empty set is a subset of S cross S. So we're interested in a relation on S. Okay. And which relation? Like that. Nothing is related to anything else. Okay. Which of the properties does nothing possess? So now we have to go through this. R, anti-reflexive, symmetric, anti-symmetric, transitive. Okay, but we really have to be careful about the logic. So, question. What does reflexive mean? It means for every element in S, okay, for every element in S, and there are elements in S, okay. By the way, you get a different answer if this was could be empty. Okay. So for every, is it in here? And the answer is no, it's not. Nothing's in there, therefore, whatever element you have in S, let's say little a comma a is not in there. Okay, so if it to be reflexive means a comma a and b comma b and little s comma little s is in there, it's not. Is it anti-reflexive? Yes, it is. Because none of those elements are in there. In fact, nothing's in there. Is it symmetric? What does symmetric mean? It says, if something's in there and you switch the order, is it still in there? Okay? And the answer is yes, it is. If something was in there and you switch the order, it would be there. But there's nothing in there, so nothing satisfies it. Okay? So this is called vacuously true. Okay? Anti-symmetric. This is complicated, so let's do it. If a comma b is in there, and b comma a is in there, does that imply a equals b? That's what anti-symmetric means. Now let's go through this. So if a comma b is a member of the empty set, it's not. And this is a member of the empty set. It's not. Okay, what is false and false? That's false. False arrow anything is true. So this implication is true. Now that's the tricky part of this problem. Okay? It's logical, but it's just nasty. Okay? Same thing for here. If a comma b is a member of empty, it's not. And b comma c is a member of empty. It's not. Does that imply a comma c is a member of empty. Well, this is false, this is false, false and false is false, false arrow full, anything. This is false too, by the way, but false arrow false is true. So yes, it's transitive. Okay, so that's very interesting. No elements, and it has almost every property. That's very, very interesting. Great, next. Number 9, B. Look at the universal relationship. Okay, so now we're going to talk about another relation, U, which is really S cross S. Everything is related to everything else. Everything is related to everything else. Okay, every element in here is related to every other element in here. Question, is it reflexive, anti-reflexive, symmetric, anti-symmetric, transitive? Okay, so let's go through it. If everything is related to everything, including little a comma a, little b comma b, whatever elements are in there, are they related? So yes, it's reflexive. Is it anti-reflexive? Well, if it's reflexive, it can't be anti-reflexive. Is it symmetric? If a is related to b, does that mean that b is related to a? And the answer is yes, because b, everything is in there. So anything after the arrow, the implication is true, so it's true. Is it anti-symmetric? Okay, well, that depends. It could be anti-symmetric. If there's only one element here, then it could be anti-symmetric. Okay, because if there's one element in here, let's say S is equal to the set A. So then A comma A is the universal relation, and it is. But let's say S is two elements. S is equal to A comma B. So then A comma A is there, A comma B is there, B comma A is there, and B comma B is there. Okay. Now, in that case, AB is in there, BA is in there, but they're not equal. So I think this is a mistake. I mean, whatever, there's two possible answers to this question. Okay, is it transitive? Yes. Why? Because I don't care what you have, if the, if we always have that if this is true, if this is 0, then this is definitely 1, right? No matter what. False implies anything. Okay, so this is definitely 1. But there's another rule also. If this is definitely 1, then this implication is definitely true. Okay, so everything's in there, therefore the transitive is in there. So that takes care of that. Okay, next. Okay, number 13. 13's not easy, but we can do it. We have the ability. 13. Okay, let R1 and R2 be relations in this. So you have a set S. You have R1 is a subset of S cross S. You have R2, which is a subset of S cross S. Okay. And now we want to know R1 and R2, this is part A, are symmetric. What does that mean? That means for every element here, for all A member of S, A comma A is a member of R1, and A comma A is a member of R2. Question, is R1 intersect R2 symmetric? I'm sorry. First we do reflective. Reflective. Okay, so what does it mean to be reflective? That means every element is related to itself in R1, and every element is related to itself in R2. Question, R1 intersect R2 is reflective? Okay. That means all the ordered pairs that are both in R1 and in R2, are they there? Well, if you look at all the ordered pairs, AA is in here and AA is in there, therefore it's in the intersection, therefore it's reflective. Yes, it is. So AA is a member of R1 intersect R2. Okay, let's do B. Okay, let's see. Okay, if A comma B is a member of R1, and that implies B comma A is a member of R1. This means R1 is symmetric. Okay, that's exactly what it means. Great. Now, R2 is symmetric means if A comma B is a member of R2, that implies that B comma A is a member of R2. Great. Okay, that's exactly what it means to be symmetric. Good. Now we assume these two things and we ask the following thing. Is R1 intersect R2 symmetric? Okay, that's a good question. Is R1 intersect? In other words, the ordered pairs are both in here and that are in here and in here. Okay, great. So assume, let's see if it's true or not. If A comma B is a member of R1 intersect R2. Question. So I'm going to put a question mark on it. I'm going to see it's correct, but I'm going to put a question mark. Does that mean that B comma A is a member of R1 intersect R2? Okay, this is a little bit tough. Ready? If A comma B is a member of R1 intersect R2, in other words, if A comma B is in both of them, does that mean that B comma A is in both of them? And the answer is absolutely yes. Why? Because A comma B, B's in both of them means it's in R1, okay? And it's in R2. Well, if it's in R1, then so is this in R1. And if it's in R2, that means so is this in R2. So this implies that B comma A is in R1 and B comma A is in R2. And that's exactly what this says. So yes, it's true. It is true. Because if it's in here, that means it's in both of them. Each one is symmetric. That means it's in like that. Therefore, they're in both. Okay, let's do C. It's the same idea. Might be a little bit more complicated. Same idea. Ready? It says as follows, R1 is transitive. This is C. Okay. What does that mean? That means if A comma B is a member of R1 and B comma C is a member of R1, that implies, this whole thing implies that A comma C is a member of R1. Very good. Next, R2 is transitive. Okay, what does that mean? Well, it means A comma B is a member of R2, and B comma C is a member of R2. This whole thing implies that A comma C is a member of R2. Great. This is what we're given as true. Okay, this is what it means for R1 to be transitive. This is what it means for R2 to be transitive. Now we ask the following question. Is R1 intersect R2 transitive? Is R1, okay, that's the question we're asking, okay? And the answer is, okay, we want to know what does it mean to be. So we ask the following question. If A comma B is a member of R1 intersect R2, which means it's in both of them, and B comma C is a member of R1 intersect R2. Question, does that imply that A comma C is a member of R1 intersect R2. That's what this being transitive means. Okay? If A comma B is in both of them and B comma C is in both of them, does that mean A comma C is in both of them? And the answer is absolutely yes. Because if A comma B is in both of them, that means it's in here and it's in here. Okay? And if B comma C is in both of them, that means it's in here and in here. Both of these are true, therefore these two are true. And what does that mean? That means A comma C is in R1 intersect R2. So it's transitive. Okay? Lots of symbols, but the intuition is very good. Okay? Finally. Okay. R is a relationship on S cross S. Now we want to look at R inverse. This is also a relationship on S cross S. Okay? That means you swap the elements. Prove R is symmetric. Okay. R is symmetric if and only if R equals R inverse. Okay, so let's see what this says. This says if A comma B is a member of R, that implies that B comma A is a member of R. Okay, great. Now, let's assume this is true. So let's see what this says. Okay, if A comma B, so we're proving it this way first. Okay, what this says is, if A comma B is a member of R, then B comma A is a member of R. But this implies that B comma A is a member of R inverse. That's what the definition of R inverse is. Take the elements, swap them. So look what it says. If A comma B is a member of R, that implies that B comma A. So what that means is that if AB is a member of R, then BA is a member of R inverse. So they're both going to be in there. AB is going to be in there and BA is going to be in there. They're both going to be there. Okay? Same thing the other way. If everything that's in here is also in here, if everything that's in here is also in here, that means, well, these two sets are equal. So if everything is in here, well, what's in here? Well, if AB is in here, then what's in here? BA. So that's exactly saying it's symmetric. If they're equal, that means what's ever in here, the inverse is in here also. Well, that's symmetric. So if this is in here and this is equal to the same thing as there, and this consists of ordered pairs backwards, so then it's also in there. So this means it's symmetric. Okay? You can be a little bit more formal with this, but it doesn't make a lot of friends. Okay, last one. Prove that R is anti-symmetric if only. So let's do this. R is anti-symmetric if and only if R intersect R backwards is equal to, is a subset of E, where E is equal to those things that are related to themselves. Everything related to itself. Okay, so let's do this. What does anti-symmetric do? We're going to be a little sketchy about this. It will be sketchy. Okay, ready? Anti-symmetric, it's something you really have to think about. Anti-symmetric means if A comma B is a member of R and B comma A is a member of R, that implies, that whole thing implies that A equals B. Okay? So let's go through that. Okay? If A comma B is a member of R and B comma A is a member of R, then that's exactly what anti-symmetric means. Okay? That's exactly what anti-symmetric means. Okay, let's go this way. It's almost, you can almost read it. Well, look what it says. If A comma B is a member of R, that means it's in here, and B comma A is a member of R, what does it mean B comma A is a member of R? Well, that means it's in the inverse too. Okay? What's the inverse? It's those things where that's AB is in there, but with the order swapped. So that means that. So that means it's a member of, let's say, am I saying this right? R inverse. Well, the only objects that are both in AB and their inverses in AB are those things that are a subset of ordered pairs of themselves. So the only way AB and BA is in there is if A and B is this special subset of only just the same things. Okay? Anyways, it goes the other way also. Okay? Namely, what does it mean that an element's in here and it's the same and it's also in the inverse is in there, that the only way that happens is they're both in equal to each other. Both being equal to each other, that's just saying that A is equal to A. Okay, so that's a little bit harder to see. Got to think about it for a while. Okay, that takes care of that. Hope you had a good time. These were not hard. This is just a lot of technical details. Not a lot of insights going on here. But anyways, it's a nice section and we did it. Have a great day.